Hello everyone, and thank you for being here. We're going to continue a little more to chat about the topic of reinforced concrete structures. With this next video, we're going to chat a little bit more about slabs specifically. Thank you so much for being here. You could be anywhere else to dedicate your time, and I appreciate that you're here viewing this video. I hope it helps. Let's get started. Very well. So the idea, first of all, is that I want to make sure to everyone viewing this video what I mean by slab, or slabs in general, okay? And I'm showing two images here. If you've seen some other videos related to reinforced concrete structures that I've made, you might recognize the images. But regardless, what I mean by slab or slabs are these flat reinforced concrete structures. So whether you're standing on them and you can call them floors, or whether you look up to them and call them ceilings or roofs, that's what I'm referring to when I'm saying slabs. So big, flat, reinforced concrete plates that you can sit on, stand on, walk on, or look up to, okay? Now, in general terms, concrete slabs, there are many different kinds of them. And I think we should start first by kind of defining some of the nomenclature related to slabs. In general terms, according to your textbook, you have ground-supported slabs, reinforced concrete slabs that is, and elevated slabs. Ground-supported slabs, as the name implies, are slabs that are poured against the ground. And that is not just any ground, so any soil, but it's prepared soil, as we'll see in a moment. Your textbook distinguishes ground-supported reinforced concrete slabs. It distinguishes between isolated slabs and stiffened slabs. Now, the nomenclature is okay from a textbook point of view for your specific textbook. I think a better way to look at it is this. If we look at them from a non-structural or structural perspective. An isolated slab, as we'll see in a moment, we'll consider that as a non-structural one, and a stiffened slab, it's better if we define it more as a structural slab. But in general terms, getting back to ground-supported, the idea of a ground-supported slab is a slab where it's generally poured against a prepared layer of soil under it, okay? So there is no space really, other than minor, between the slab and the soil under it. Now you can't just have any soil, right? And it can't just be the soil that you find on a site. That soil needs to be prepared, and needs to be adequate, it needs to be appropriate. Here's an example taken straight from your textbook about what a good way to pour the slab on prepared ground would be, and that is that you would first have a vapor retarder right under the slab. And then here it shows a 4-inch band of sand subbase, but normally any appropriate non-frost susceptible granular material of some sort is adequate and acceptable. And then the ground under it needs to be flattened and compacted. Okay, it can't just be any ground. When it comes to elevated slabs, well, we're going to chat more about that once we're done covering ground-supported slabs. So let's talk about ground-supported slabs first. Let's start with isolated, or what your textbook calls as isolated, and I would prefer to define for us as non-structural slabs. These are slabs, again, that I'm defining as non-structural. What that means is that the structure above, the building above, is actually not being supported by this slab, okay? The slab is actually not holding up any of the columns, any of the walls, in such a way that if the slab were to suddenly disappear, the integrity of the structure and building above it would not be affected. Okay, it would not collapse on you. That's what non-structural means. Ground-supported slabs, if they're isolated, that is non-structural, they must be reinforced still, even though the reinforcing is mostly to prevent unnecessary and unsightly cracking. Okay, it's not to avoid cracking 100%, but to keep it to a minimum. The reinforcing, as you can see here, typically is done in a matte fashion, like a hashtag, if you will. So it goes parallel and perpendicular to the direction of the slab. And the idea is the isolation is that you want to isolate the slab from the actual structure that comes down. So you see these blocks that I'm showing with an arrow, that's where you're going to pour the footings of the columns, okay, that come down on that slab. That way, the slab itself is actually separated from the footings, which are structural, right? They're actually holding up the slab. And then with ground-supported slabs, if they're isolated, that is non-structural, you also want to make sure that you insert control joints, which is basically a way of forcing the formation of cracks in locations you want them. I'm going to link for you at the bottom a video that's already been made for you related to control joints, sizing them, and it relates to this image that I just put up for you, figure 22.38. But the main thing that I want to point out too is this. This is an image that I've taken straight out of your textbook, and it's the next step in the pouring of this non-structural slab, right? The space that's been left out there is where the footing of the column will be. Well, this doesn't quite apply to Canadian construction, and that's because in Canadian construction, you have to build typically the structural portion of a building below a slab, even if that slab is on ground level. And that's because in Canada, you have to deal with frost, right? You have low temperatures, and you have to put the structural portion of something below the frost line, unless you do some other stuff. Now, a final thing that I want to let you know basically about an isolated or non-structural slab is an identification of what the purpose is. The sole purpose of what your textbook calls an isolated slab or a non-structural slab is to provide a comfortable walking surface or storing surface so that occupants can walk on a nice clean surface rather than the ground below it. There is no other reason for it, okay? It's comfort. Now let's talk about what the textbook identifies as stiffened slabs and what I would like to rather define as structural slabs. They are structural, so that means that it's actually holding up the structure above it. If that slab were to disappear or be compromised, it would compromise the structure of the building that's above it, okay, that's being held up above it. It must be reinforced in a manner that's superior to simply isolated slabs or non-structural slabs. So you do have reinforcing that's going perpendicular and parallel, and it also has to be placed properly to account for the tension and compressive forces that this slab has to resist. It is supporting the structure, okay? It's structural. So this slab is critical to ensure that the rest of the building above it stays safe, is strong enough. Typically, you don't have control joints in a structural slab like this one. There can be referred to, typically in Canadian construction, you'll hear them referred to as structural slab, raft slab, engineered slabs. And for the most part, in Canadian construction, they're used for light loads, okay? And by that I mean light loads associated with, say, a one-story Part 9 building. And the reason for that is because, again, in Canada, we have to deal with frost. So you have to build down enough to avoid the effects of frost on a building, right? On the footings and foundations, the lowest part of your structure. And to do that for a structural slab, it means preparing the soil to a fair bit of depth below it. Now at this point, excavation costs related to construction are such a small portion that simply digging down deep enough to put your footings below frost grade is way more cost effective than the extensive engineering analysis and design that's required to actually do a slab rather than a foundation and footing type design. So that's why typically structural slabs are not used in Canada typically for anything more than light loads. And by that I mean a one, at most, a two-story Part 9 type building, okay? Now, let's talk a little bit of the how-to related to ground-supported slabs, and that is, how are they made? First of all, you have to prepare the base, okay? You can't just pour concrete directly on soil. The soil has to be prepared. You want that soil to be flattened, level. You want it to be properly compacted. And you want it to have the layers under the slab that I showed on the previous image, right? These ones here. So you want some granular material. Here it shows 4-inch sand, but you can put whatever granular material that ensures proper drainage of the soil so that you don't get frost happening. And then maybe a vapor retarder between that and the slab underneath. You'll find it in construction in Canada too. There should be also now a layer of rigid insulation, of insulation of some sort under that slab if it's a heated space. Forms. Because, as you know, concrete is shapeless, you need to form that slab to give it a shape. Kind of like you see here. I took this figure directly from your textbook, as you can see referenced. Then you have to reinforce it, right? With parallel and perpendicular slab. It's basically a hashtag type pattern. And finally, you pour the concrete and then you cure it. That is, you let it sit under appropriate conditions so that it hardens and it gains strength. That's how you do a ground supported slab. Let's talk now about elevated slabs. I took this image straight out of your textbook to show you the different kinds of elevated slabs. They're roughly distinguished in beam supported slabs or floors and beamless floors. But elevated slabs are basically those slabs that are made and they're not against the ground in some fashion. That is, an elevated slab you can walk under and look up to say, hey, I see a ceiling. Okay? Now let's start with beam supported elevated slabs. The only way to tell if the elevated slab that you're looking at is beam supported is to look to the underside of it. That's the only way, and hopefully the structure is exposed so you can tell. So I posted here for you. You can see an image that I took straight out of your textbook. You can see that there is a slab that's supported by beams that typically span from column to column, but not always. Okay? Each one of those slabs is identified by having beams basically as the perimeter of that slab. Now you see that each one of those slabs had a one-way slab, two-way slab showing on it. What's that all about? Well, I'm going to talk a little bit about it and then remind you, as this little finger is pointing down, that I've made another video related to one-way slabs and two-way slabs and how to identify them. Basically, whenever you find a slab, an adequate rule of thumb is this. You take the long dimension of that slab, you divide it by the short dimension of that slab, and if that number is more or equal to 2, that slab is considered a one-way slab. If it's less than 2, it's a two-way slab. Now, in that video that I've linked for you, I also go through explaining how this is a rough rule of thumb. The reality is you can't tell if it's a one-way slab or a two-way slab unless you know the reinforcing pattern, which is invisible to you, okay? But I talk more about that in the video below. Now, instead, what I want to do is talk a little bit about what the difference is between a one-way slab and a two-way slab. So let's do that. A one-way slab is the kind of slab that behaves in this fashion as you see right here. That is, because it's much longer in one direction than it is in the other, it bends like a barrel, okay? Like a half pipe, if you will, so that all the forces on that slab gets distributed only along two sides of that slab. That means that the load on that slab then gets transferred to the beams or walls on the side of that slab. That's different from a two-way slab. A two-way slab is such that instead the sharing happens more evenly along all four sides of that slab, as you can see here, so that the loads on that slab are distributed on all four sides. They go to the beams on all four sides, if there are beams, and then the beams pass on those loads to the columns. Okay, so that's the main difference. A one-way slab has what's called a one-way bending. It bends like a barrel. A two-way slab bends like a trampoline. It bends in two directions. Okay, it bends parallel and perpendicular. Okay? Now, I'm going to link these videos for you below. I'm also going to link for you an interesting article that I found. It's written in plain English, which I love, right? And it kind of gives some more details and information about one-way slabs versus two-way slabs. And it's linked for you as extra information. Now, some rule of thumb related to slabs. Typically, the bigger the span of the slab, the thicker the slab has to be to ensure that it's safe. And by that I mean strong enough and safe enough, right? That it makes you feel comfortable. It doesn't deflect too much. Typically, one-way slabs should be up to a span of about 4.8 meters. Two-way slabs up to a span of about 7.3 meters. If you want spans of slabs that are bigger, you want to start adding beams and girders to ensure that the slab is long enough and maybe to reduce the thickness of that slab. The only thing is though, when you start doing stuff like this, you increase the price of the structure, okay? Because with reinforced concrete, you pay for the shaping of the structure, the forming, you pay for the reinforcing, and you pay for the human labor time associated with that. Okay? The expensive part in reinforced concrete structures is typically considered the forming, okay? Because it has to be, it's usually custom, usually, okay? Now, some rule of thumbs related to beam-supported one-way slabs. I took these straight out of your textbook. When you have a beam and girder supported one-way slab, like what you see here from Appendix B, page 959, typically the biggest span between beams for this kind of setup is between 2.4 and 4.6 meters. And what I mean by span of the beam is the distance between the beam members that are being supported on those girders, okay? In terms of column spacing for one-way band beam slabs, again, take straight out of Appendix B from your textbook, your column spacing can be anywhere from 7.6 to 9.1 meters. Okay? And then for this one-way joist slab that you can see here, the column spacing can go up to 7.6 to 12.2 meters. Okay? And that's because with the addition of all these extra joists, it makes the floor stiffer and it can be wider and bigger. When it comes to two-way slabs, some rules of thumb. Column spacing for a typical two-way slab is anywhere between 6.1 and 7.6 meters. And that's usually in both directions, because for a two-way slab, you want the distances of columns on both sides of the slab to be close to the same. Column spacing for a waffle slab like this one here actually goes up, right? Because you have a lot more beams that are supporting and making this slab stiffer. So it goes anywhere from 9.1 to 13.7 meters. But here's the thing, the cost skyrockets because there's a lot more work involved with doing a slab like this. Typically, these slabs are not made anymore. They're not built like this anymore in Canada. It's too expensive, especially given that you can get the same result by simply readjusting the reinforcing, slab thickness, and the location of the beams. Okay? Now, for some beamless slabs, rule of thumb. Beamless slabs have no beams between columns. So for the flat plate, you see here on the right-hand side at the top, I took this straight from Appendix B. Column spacing can be anywhere from 4.6 to 6.1 meters. Okay? For the bottom one, for flat slabs, the column spacing actually can go up from 6.1 to 9.1 meters. And what's the difference? The drop panels, right? Remember these, the drop panels? If this doesn't look familiar, then I've linked for you a video that we've done before related to drop panels and what their purpose is and why they're built around columns. So go check that out. That has some interesting information related to that. So how are elevated slabs made? Well, in a manner that's very similar to slabs on ground, except that you don't have to prepare the ground because they're not poured against the ground. So instead, you prepare the base for it. And the base for it is usually a form of some sort. I'm showing here in figure 2210 from your textbook an example of a flying form. So this is a form that's a solid flat piece properly built that is about the size of the floor or slab you're about to pour. Another possibility is that you build up that form, that flat base, custom, okay, for every application you're doing. Don't forget that again, for reinforced concrete, the forms typically are the expensive part for this, okay? Then you place the reinforcing, and that's in the parallel and perpendicular direction. Then you pour your concrete and let it cure so that it reaches the desired strength, right? It goes from fluid to solid, and you're good to go. What I would like to talk about before wrapping things up is this concrete cover. And I'm not talking about the action that you do when you're in bed of pulling a blanket or a cover over you, although it is very similar, okay? What I mean by concrete cover is the layer of concrete that covers the steel that is closest to the surface, okay? So the reinforcing steel in concrete cannot be too close to the surface of the concrete. Otherwise, any moisture, water, or any other type of elements could affect that reinforcing steel, get it to rust, and adversely affect the properties of the concrete and the integrity of your structure. So as you can see here, you see these elements here, these chairs. I took this image straight out of your textbook, figure 2225. Their purpose, in this case, as it's shown here, is to lift that bottom layer of reinforcing steel from the ground, right, so that there is a concrete cover at the bottom of that slab to give a minimum distance between the ground and the closest steel along the bottom. You would do the exact same thing also for that layer of steel at the top of the slab that is closest to the top surface of the slab. You want to give a minimum distance so that then you can cover that steel with a layer of concrete and ensure it is properly distanced from the outside elements. You can find the details of the minimum amounts of concrete covers in your textbook, table 22.1. Great. I want to leave this as, I guess, the end of the topic of slabs, and this is for cast on-site concrete. I'm gonna make another video related to precast concrete slab and structures and pre-stressed post-tension concrete slab and structures. But that's gonna be a different video that's gonna be linked for you at the bottom. Other than that, I wanna thank you so much for your time. You could have been anywhere else and you chose to be here. I hope this video has been helpful for you, and don't forget to check out the videos linked for you at the bottom of your screen. Thank you so much, and have a great day.